Hey everybody, and welcome to another probably private red teaming edition. It is officially cold and hoodie season here. So if you want, tell me where you watch probably private from, but to make sure that you at least partially pseudonymize or anonymize your responses. I look forward to seeing your attempts to write locations anonymously. Okay. Today, as promised, we're diving into training data. And why should we look at training data? Well, A, because it's definitely in the model somewhere. And B, I think training data and thinking through what goes into training data can give us a good idea of how to exploit the model as an attacker. And then it's also certainly something we need to think about when we're defending. So we need to be aware. What do we think the model learned, right, or stored in a variety of ways, shapes, and forms? And then how do we exploit that? And then how do we eventually defend that? So we're going to shortly be moving into defenses as the next part of the mini course. But today we're taking a look at what's actually in our data. And the first thing that we're going to do that is we're actually going to take a look at embeddings. What are embeddings? You probably heard about this already, but embeddings are the way that we take kind of human interpretable data, right? Encoded for a computer so that we can load it digitally and see it on our screen, right? And how do we take that information, that data, and represent it in a way that helps us learn? And embeddings for vision are different than for text. And you might have, in building your own, let's say, RAG systems or working with LLMs, you might have heard about document embeddings or text embeddings. And today what we're going to do is we're going to explore those from an adversarial point of view. And so we're going to load in some text vectors. So this will take a minute to load for you if you're loading it for the first time. And this is a really popular embedding library from the Meta team, from Facebook, called FastText. And depending on your compute, this may or may not run. So please let me know if you have problems running this. But we're going to take a look at these embeddings. Now, what exactly is an embedding? For text embeddings, for word embeddings, which is what FastText kind of works in this space, essentially, you can think of it as a really dense representation of the word as a member of all of the words that Facebook decided to put into this model. So we have all of the words that exist in whatever data was used to train this embedding model. And then based on the relationships of how the words show up together, then we create this embedding, which is a dense representation of the information from that word. And in image, they have different ways. Often in image, instead of taking one image and making an embedding, just like, you know, a word is not a full piece of text. If we go word by word, it's chunk by chunk. In imaging, they also go chunk by chunk. So here's the first box of the image, then the second box of the image, then the third box of the image, and so on and so forth. And so this chunking of data and then training a way to embed that properly, or in image, because they have limited space compared to what we do with language, they can just feed chunk by chunk in. Anyways, neither here nor there. If you work in image and I got it wrong, then yell at me in the comments. Silly language people. Anyways, so here we go. We got our dense representation. I was reading some really interesting reporting about the, like, quote unquote manosphere. And I was curious today in exploring, if I was thinking adversarial, I'm like a new up and coming manosphere influencer. Like, you can totally picture that, right? Anyway, if I'm a up and coming manosphere influencer, how might I, use LLMs to my advantage. So we're going to talk about topics around that today. So like money, right? Like I want to convince people if they follow me, they can get lots of money. Here's my embedding for money. Obviously, it doesn't really tell me anything, but it does start to tell me something if I start poking around. What's near me? I'm money now. What is near me in vector space, in tensor space, right? So I'm going to take a look. What are my nearest neighbors? And here you can play around with this, choose K of your liking. So here, similar to what we talked about, look, we got noise in the data set. We got the top one is money misspelled. The second one is money but. Money so. Money's money now. Money and. Moolah. Ooh, I like that one. I forgot about that word. Okay, so we can look at our nearest neighbors. If you want to explore some other words now, is a good time to pause. You can just play around here, see what words you want to use. You could go back to our computer virus. You could go to any topic that you want to explore. But have a look around. What are your nearest neighbors? And then I was thinking to myself, oh, but there's like this difference between like money and capital. You know, capital is like when you got big money. Money is just like, I got 20 euros, you know? So I was curious, what's happening around capital? But of course, disambiguation, capital can also be like capitalization, right? Like there's a few different things around capital, right? So we see capital, capital the, capital in, but this capital, maybe that's part of venture capital, right? So we can take a look here. So that's interesting. And then we have a way which you might have already explored if you're looking at building things like RAGs or search, or even if you're just doing evaluations of your LLMs, you might have heard about cosine similarity. And cosine similarity can range from -1. We think the two vectors or embeddings are totally opposite. 1, totally the same, and anywhere in between. And we can also start looking at things like Euclidean distance, which we can think of in some sort of massive vector space as the hypotenuse. If I go from the tip of this vector to the tip of that vector, how far are they from each other if I can just fly through dimensions? Okay, hopefully that was a useful explanation for you. So I wrote a little thing that can take our words and our FastText embeddings and look at cosine similarity. Remember, 1 is totally the same, -1 is totally the opposite, presumably, if our embeddings work correctly, which of course we can question. Okay, money enriched 0.30, money capital 0.32, money wealth 0.44, money pores 0.37. So now we're starting to get some interesting information about our training data. Money and pores is technically with cosine, and cosine isn't always the best measurement, so interpretations here can vary. But money and pores is technically showing up closer together in the text that Facebook trained on than money and capital, and certainly more than money and rich. What are we learning? Ideas, comments. What do you think this is showing? Very curious to hear your inputs. And we can also then take a look at the Euclidean distances. And so here we also see money and rich is further apart than money and pores. By Euclidean distance, money and capital is closer. So here we can see what distance you use matters. There is plenty of debate of what distance is best. Until you really understand how you're wanting to use distance, I would say measure both and think about it for a while. Eventually, for whatever your use case is, for whatever you're trying to do, hopefully it will start to become apparent which distance is most useful for whatever you're trying to do. And there will be some upcoming videos next year, or I don't know when you're watching this, but soon on how do we actually think through evaluations from a privacy and security perspective, and we'll come back to this topic then. And another thing that we used to do quite often that's certainly less done today is to try to create a projection into a lower dimensionality. Now, this is also riddled with problems because, as you can imagine, we're taking words, we're projecting the words into a smaller dimension, which is creating these vectors. So we already have essentially compression, right? And then now we're taking these vectors and we're trying to project them down to a small space, let's say like a 2D or 3D space. And this is usually used so that we can visualize and notice interesting things that might be happening in our vectors, right? So this is, again, to teach us as humans, is this happening correctly or not? Am I interpreting what the model has learned correctly or not? Did the model do what I wanted it to do or not? And what I'm going to show you here is tSNE, which is one of the popular algorithms for this type of projection, which again doesn't always tell us if the model's doing what it is, but is one possible way for us trying to inspect and take a look and use our human brain again to see, is the model doing what I want? And here I tried to, I was doing my reading, so I try to find some words that if I'm building this like influencer bot, what are some words that maybe the influencer bot should focus in on? And then how do those words relate to each other in embedding space so that I can find clever ways maybe of generating text using these as kind of seed words or seed vectors. And I was surprised by this because we don't even really have a huge cluster here. Now, probably if I put in a word here that has nothing to do with this, let's put in, I don't know, gardening. Let's take a look. Where is gardening? Gardening is maybe here or here. Anyways, obviously this projection is not giving us a lot of information. And so what I want you to do now, because I had tried a few other things and some of them give better versus worse. So what I'd like for your exercise this week to be is think about, particularly like what I'm talking about, like we're trying to seed, maybe we're trying to get an idea of what language we should use to do something. And remember, most of these embeddings are trained on a lot of online text. And so we can exploit things that we know about online communities. We can try to find areas of this embedding that we want to activate. And then we're going to use essentially these embedding models to teach us what's nearby. How else can I phrase this? How else could I do this? What other words do people use when they're talking about these topics? What topics are similar? What topics are further away, right? And I want you to play around with this. I want you to, if you build out a notebook, paste it here. Let me know how it went. B, let me tell you, hot tip. Go to Hugging Face, okay? Go to Hugging Face. Have a look around in the data sets. So go to Datasets. I highly recommend taking a look at this C4 data set. This is a data set that is from the Common Crawl, and there's a data viewer, so you can just have a look around. You can search for stuff. So I was doing some attacks the other day, and I was looking for stuff, but you can also just load the data set on its own, and you can just have a look around. Just look. What's in here? What's going on? What words do you want to try to exploit, right? You can page through page by page. You can search some stuff, but have a look around on what's going on because there is some interesting stuff in here, okay? So I want to know what you find. This isn't the only data sets. There's also really great data sets on prompts. There's really great data sets on computer vision. Now there's more and more data sets on video and audio. Poke around and look for things that A, you think, I don't know if I want the model to learn that. Let's have a look what it's learned about it. And B, have a look what type of words are going on the internet. Because let me tell you, if you have not looked at the internet, or if you're in an algorithmic bubble on the internet, this is one really interesting way to get yourself out of the bubble, is go look at scraped data, and you will quickly find maybe your experience of the internet is different than that of a bot. So have a look, get curious, tell me how your embedding research is going, and start thinking about how we can reason about what models have learned based on what we know about training data, and use that to, again, then also update all the other attacks that we've done. Our prompt engineering attacks, our advanced prompt engineering attacks, our model versus model attacks, because you could give a model access to this and say, go wild, right? So think through, as you learn about these common and widely used training data sets, think about how you can exploit that for your advantage as an attacker. And I'm excited to hear more from you. This officially kind of wraps up the first part of the mini course, but don't worry, we're going to keep working together, because what we're going to move into next is we're going to start to think about how do we protect our models. So now we've had a good time with our attacker hat. We're starting to think like an adversary. That's super useful, because now I'm going to flip the table and say, okay, you've learned a lot about how to attack. How do we actually start to defend? What makes sense? What doesn't? All right, so let me know how it's going for you, questions you have, other attacks you want to request at a future point in time, and get ready next week to start your defense strategy. All right, see you then.